Hello students, welcome to this lecture on interconnects, and in this particular lecture we will talk more about the crosstalk effects, and in that sense we will talk about the crosstalk in a manner where there is one aggressor wire which is affecting the other victim wire, where the victim wire is actually held to a constant voltage, and we will see what is a transient response or a transient analysis for the victim wire, and what is that magnitude of the transient response if the drivers of both the wires, if the drivers of the attacker as well as the drivers of the victim wires, if it is of a particular size, we will then try to estimate what should be the effect of the crosstalk on the victim wire. Right. So moving further, let's go to the next one. So here in this particular slide, I have just done a schematic of the crosstalks. So I've just shown the wire A and B, where so the wire A is driven by the inverter here, and the wire B is also driven by an inverter. The wire A and the wire B are it has its own characteristics capacitance and then a resistance. The capacitance CA and CB, it's its own characteristics capacitance, which is seen here. Because the wire A and B are close to each other, then we'll say that we also incorporate the adjacent capacitance or a coupling capacitance here. I'm labeling the aggressor for the wire A and then the victim for the wire B. So the changes here made for the wire A, or rather, the changes made here in the driver circuit is going to drive the changes in the wire A, and that is going to get coupled to some extent to the wire B, which is held constant. So an input to this wire B's inverter driver circuit is held constant to logic level high. So the output will be held constant to 0. So that means that this particular wire which is connected to the output node is actually pulled down to the ground via the NMOS transistor, via the always on NMOS transistor. So in that sense, this particular wire is kind of connected to the ground via the NMOS transistor. Here, there is a change in the input 1 to 0, and that's why there is a change in the output from 0 to 1, and we need to know what kind of an effect it will have on the wire B, although the wire B is connected to the ground via the NMOS transistor. Right. So again, CA and CB and C adjacents are the capacitances associated with the dimensions of the wire A, B, and its the neighboring dimensions. Right, the neighboring dimension in the sense the spacing between the wire A and B will be able to characterize this C adjacent capacitance. So hope this is clear. So if I want to represent this wire A and wire B in terms of the R and C circuit, so I'll use a very simple model, L model, on both the wire A and B, and in between there is a coupling capacitance or an adjacent capacitance. So this dotted boxes represents the same. It is an L model of the wire A, and then another dotted boxes is the L model of the wire B. Inside the dotted boxes, we see the resistance RA and then the capacitance CA. Similarly, for the wire B, we have the capacitance CB, and then the wire RB is actually connected to the ground. What it means is this particular switching resistance of the RB, right? It is actually there. But this particular resistance is, this resistance is nothing but the NMOS resistance and then connected to the ground. So that is what this RB represents. This is basically the NMOS one, NMOS transistor switching resistance. And for the wire A here, it is actually changing from 0 to 1. So that means assuming that it's a step input at the input side. So we'll get 0 to 1. That means the PMOS transistor is actually on, and then the NMOS transistor is off. So this could be considered as the switching resistance of the PMOS transistor. And then CA, CB, and then C adjacent is anyways taken from this particular schematic diagram. What I've ignored here is the parasitic capacitances of the driver. So the inverter's parasitic capacitance, we say that it is very, very less than that of the wire capacitances, hence that has been ignored. And the wire resistance, the wire which is of pretty long length of the wire, that is also kind of ignored. So the resistance of the wire is kind of ignored, but we have accommodated the resistance of the inverter. In fact, this particular resistance RA and RB could also be, could also accommodate for both the inverter switching resistance as well as the long length of the wire. So that is also possible, but in this particular scenario, what we say is RA and RB, it is just the switching resistance of the driver circuit. Right, hope this particular diagram is clear. Moving ahead, so if suppose I have this particular, the RC circuit, and if there is a delta VA, so which is generally in this particular case will be nothing but 1 volts, right? So a change in the input will give me a change in the output. For a digital circuit, I will have a 1 volts change for a 65 nanometer technology node. So what will be its effect on the other side of the wire B? Right, so at this particular point, B point. So that is given by this particular expression. So delta VB, the change in the B node, or rather we can say it is then the victim node, and aggressor is the A wire, the victim is the B wire. So the change in the delta VB, the change in the voltage at the node B, can be seen as the change in the voltage at A multiplied by the C adjacent divided by C adjacent plus CB, and then multiplied by 1 plus K, where K is nothing but the RA multiplied by CA and C adjacent divided by the RB multiplied by CB and C adjacent. So it is basically turns out to be basically a time constant factor. So a ratio of the time constant for the wire A and its associated capacitance, and then similarly the time constant for the wire B with its resistance and associated capacitance. Right, just for our simplification, if we consider all CA, CB and C adjacent to be the same, then all these parameters will get cancelled in the sense the factor K here, the CA, C adjacent, CB and C adjacent will get cancelled, and then we will be left with RA and RB. Right, so K will be RA by RB. So my overall delta VB, so in this particular expression, delta VB in terms of delta VA will be nothing but 1 by 2, because C adjacent is equal to CB. We have considered all the capacitances to be the same. So it will be 1 by 2 multiplied by 1 by 1 plus K. So where K is nothing but RA by RB. RA by RB. Right, so this is my overall expression, a very simplified expression considering the capacitances are equal. So it becomes a, this particular function, or the delta VB, the change in delta VB with respect to the change in delta VA becomes a function of the driver switching resistance between the RA and RB. All right. So let's say this is my the aggressor wire, and then this is the victim wire. Let's say there is a change in the voltage, delta VA is 1 volts here. Because of the coupling effect, so the change here in 0 to 1 volts, let's say that it is getting 0.5 volts. So I'm just assuming some particular voltage, and I'm saying that because it's a change in 1 volts, and C adjacent and CB, everything is same. So we will have the change here, if at all there is a change here, the maximum change in the wire B, or rather the maximum change in the voltage with respect to the wire B will be 0.5. So if 0.5 goes here at the output side because of the coupling capacitance, although it is held at 0 because of the NMOS transistor which is connected to the ground, so this 0 voltage is constantly pulled to the ground, but because there is a 0.5 voltage that is kind of coupled from the neighboring wire, so what should be the switching resistance of RB or the driver B, and what should be the switching resistance of the driver A? In this case, the drivers are nothing but the inverter circuit, so we need to find out what is the switching resistance of the inverter on the A wire, and what should be the switching resistance on the inverter that is there on the wire B. To find out the switching resistance, what we need to know is what is the output voltage changing from, right? So in this aggressor line, the output voltage is actually changing from 0 to 1 volts. In the victim line, the change in voltage is actually 0.5. It is actually held constant at 0 volts, but because of this coupling capacitance, we will get a 0.5 voltage line. And then once again it should discharge, get, this 0.5 voltage should be discharged to 0 volts. Right, so the output voltage is actually 0.5 to 0. In this case, because it's a PMOS on the A side, it is a PMOS transistor which is making this change from 0 to 1 volts at the output side. So if I consider the inverter here, the PMOS is on and the NMOS is off, right? And that's the reason why we are getting the output voltage from 0 to 1 volts. So in that sense, if the PMOS is on, so the switching resistance is with respect to the PMOS transistor. And if that is the case, then the VSD of the PMOS, the output is 0. So the VSD of the PMOS, so let me draw the PMOS circuit and then the NMOS circuit. And let's say that this is my driver on the A side. So this is my output on the A side. And the output is actually changing from 0 to 1. All right. So the VSD, so the source here and then the drain here and then the gate here, right? So the VSD of the PMOS, when it was at 0 volts, the output was 0 volts, we got the VSD as VDD. So that is what it is. And then when it became 1, the VSD was 0. So that is a change here, VDD to 0. So if I try to find out the switching resistance for the transistor, PMOS transistor on the A side, on the aggressor line, we can note it as RA. And similarly, if we do the same thing here on this side, but on this side, it is actually the NMOS transistor. So let me draw the inverter, VDD. And here is the output. The output is actually constantly going to the connected to the ground because the NMOS is on and then the PMOS is off. But because it sees 0.5 line here at the output line, 0.5. So there is a 0.5 voltage coming, or coupling from the wire A side. So let me, instead of this one, I'll say that this is 0.5 volts. So the 0.5 volts is going to get discharged to 0 volts, right? So my output is at 0.5 volts and then it will go back to 0. So that means that the VDS value, VDS, so of the NMOS, VDS will be 0.5 to 0. And my switching resistance is considered as RB. So now what we have done here in this particular slide is we estimated the switching resistance for the aggressor line, so the driver on the aggressor line, and estimated the switching resistance on for the driver on the victim line. And the switching resistance for the driver on the aggressor line turns out to be RA, and the switching resistance for the victim, for the driver on the victim line is stated as RB. Let's say both the driver widths are same. So on the aggressor and victim side has the same widths, right? So in the same widths, so if I have the same width here, right? Just that the output voltage is different and thereby my VSD value and VDS value are different. My RB, right, is going to be half, approximately, I'm taking a very approximate measure, because the voltage for the B side is actually 0.5 to 0 volts, and here on the A side it is actually 1 volts to 0 volts, right? If I'm talking about VSD on the PMOS side and then VDS on the NMOS side. So the change in voltage is actually exactly half, right, from the B side to that of the A side. So we can consider that the RB is actually half of that of the RA, right? If the sizes are the same, if the width of both the inverter circuits or the driver circuits are same, right? So what we have is RB is equal to RA by 2 if the widths are same. So in that sense, the K value, which is nothing but RA by RB, right, will be nothing but the value 2 if it is of the same size. If it is different size, we will have a different ratio, right? So in that sense, delta VB, which was nothing but as a function of delta VA or whatever, delta VB by delta VA is equal to 1 by 2 and then multiplied by 1 plus K. And the K is nothing but 2 for the same size. So it turns out to be delta VA by 6, which is nothing but, so it is actually 18%, right? So the 18.88% of the delta VA. So a change in 0 to 1 volts on the A side, on the aggressor side, will have an effect of 18%, so 0.18 volts on the victim side. So now let's take case by case and also see some cases where we have a different widths on the driver side for both the aggressor and then the victim line. So let's say that when the victim is floating, so that means that there is no driver inverter circuit at all. So we will have RB is equal to infinite. So the switching resistance when it is actually floating, right? There won't be any switching resistance, and in fact we can say that it's an RB is equal to infinite, right? It's an open circuit kind of thing. So RB is equal to infinite. So if RB is equal to infinite, K value is nothing but RA by RB. Right? So in that sense, the K value is 0. All right. So the K is equal to 0 represents delta VA. Delta VB is nothing but delta VA by 2, and then 1, and in the denominator we had 1 plus K, where K is equal to 0. So it turns out to be 50%. Right. So this is the case 1 when the victim is floating. What it really means is it is not connected by any driver circuit. Right. So what I can draw one figure for the line. So this is the wire A. And then the wire B will be something like this. So there is no driver circuit that is connected, and it is it is like that. It's a simple wire, but it has the coupling capacitance C adjacent, and this wire will have CA capacitance, and then this wire will have CB capacitance. Right. So in that case, if it is not driven by any inverter circuit or any circuit here, any logic gates here, then we will have the voltage due to the change here from on the wire A side, which is driven by this particular inverter, turns out to be 50% of the delta VA. Right? Remember that this 50%, because it is held floating, so we will have a constant 50% voltage here. So this particular, if it was held at 0 volts, so this is going to jump to 0.5 volts here if it is the change of 0 to 1 volts here on the wire A side, on the aggressor side. So we'll have 0.5 volts, and this will be held constant. Right? If it was driven, as we had seen in the last case, if it was driven by another inverter, then the NMOS was constantly on, and even though if it reaches whatever voltage, it should come back to the 0 volts. Right? Hope that is clear. Let's say the second case, when the victim is driven by an inverter, victim's inverter is half the size of the wire A. So the size is less. That means that the resistance with this particular half the size should be equal to, will be more than that of the resistance when it was of the same size. Right? So in that sense, RB should be equal to RA. Right? So in that case, the K value turns out to be 1. And I will have delta VA by 4. So delta VB, the change in the voltage in the victim line side will be 25% that of the change in the aggressor side. So you will have a 25%, but because there is an inverter which is constantly driving this wire, so even though there is a 25% change, it should come back to 0 volts. Right? So this change will be, the maximum change will be nothing but 25% of the change in the aggressor side, which will be 1 volt. So it is 0.25 volts is what we should be able to get as the maximum change. Third case, when the victim is driven by the equal size inverter, and this is what we had seen. So it turns out to be 16.67%. So sorry, I had said 18%. So it turns out to be 16.67%. So this is 16.67%. So delta VA by 6 for the change in the voltage. And if it is driven by the inverter, then again its change will be 16.67%, which will be 67%. So it will be 0.16 volts will be the maximum if the change on the aggressor side is 1 volts. Lastly, when the victim is driven by the inverter of double the size, right? So if it is the victim is driven by a double size inverter. So that means my RB, right, is actually very, very small now. If it was of the same size, we had RA by 2, right? Now the size itself is double, so we should have a much lesser resistance, and by the long channel model we can easily scale it and then say that it is RA by 4. So my K value turns out to be 4. So my delta VB is nothing but delta VA by 2 into 1 plus 4, which will be 10, so it will be 10%. So 10% means I will have a change of 10% and then coming back. So this change will be 0.1 volts. If the aggressor line voltage change is 1 volts. So finally, what I've drawn here is for different cases of the victim, for the different cases of the inverter or the driver circuit that is designed on the victim side, not on the aggressor side, on the victim side, what is the transient response? So this is the delta voltage change on the y-axis, and then the t, time, because it's a transient change, so we need a time factor on the x-axis, and 1 volts and 0.5 volts and then so on. If the aggressor is actually changing, from 0 to 1 volts, 0 to 1 volts, what will be the change on the victim side? If the victim wire is left floating, there is no driver circuit, then as I said earlier, it will be held constant to 0.5 volts. So once it reaches 2.5, it will be held constant because there is no other driver circuit which makes it pull down or pull high, right? So it is not connected to the NMOS transistor and then connected to the ground, right? And so in that sense, the wire is floating, and that's why it will get charged to 0.5 volts and it will be held constant. When the victim is half the size, we got, so let me go previously. When the victim is half the size, the RB was equal to RA, K was equal to 1, and then we got a 25%. Right, so this particular change is a 25% line. So if I draw this, so this will be 0.25 volts. Right, so here you see that it goes to a maximum of 0.25 volts and then comes back to ground voltage, comes back to 0 voltage because it is driven by an inverter of half the size. Right, there is an inverter which ensures that the wire is constantly connected to the ground voltage through the on NMOS transistor. And similarly, if the victim is of equal size, we got 16.67% of the change from the aggressor line change in the voltage. And if that is 1, we will get this 0.16 voltage here if the victim driver circuit is of the equal size. And lastly, if the victim is of the double the size, we will get even lesser voltage, which is around 10%. So this maximum change is 0.10 volts, right? Hence, to reduce the crosstalk effect, to reduce this magnitude of the crosstalk effect, crosstalk, also called as crosstalk noise effects, coming from the aggressor line to the victim line, we say that the victim's driver circuit, or whatever the inverter size in this particular case, it could be a NAND gate, it could be a combinational gate. Make sure that the gate size is considered or recommended to be very high. So in that sense, we will have, if the gate sizes are made higher, then we will have a lesser switching resistance, and that is likely to give a less effect onto the, lesser effect onto the victim line.